Okay, we were solving this boundary value problem, partial differential equation, boundary value problem, the heated rod. Here it is. And in this case, the temperature was held at 0 at both ends of the rod. It had some initial temperature at time t equals 0. Here was the problem statement in terms of equation. Here is the boundary value problem. We used separation of variables or the product method. That led to two ordinary differential equations. We had canned solutions for those. And in boundary value problems, we not only separate variables for the equations using the product method, we have to use the product method on the boundary conditions as well. And that led to these two boundary conditions on our X differential equation. With this equation and these two boundary conditions, we could completely solve for the X equation. In fact, with this lambda in it, it led to the eigenvalue problem. And we, in fact, got an infinite number of solutions for the X equation. Now, what about the T equation? We had a solution for it, but now we know what the lambdas are, and we have to use the same lambda for each function, for both X and T. So that our T, we have an infinite number of T solutions corresponding to each lambda. And here are the T solutions. So we put them together, each T and each X, or each X and each T. We have an infinite number of solutions. This will be the product of the X's and the T's. Here's the T part, here's the X part. Same ends, which are all the positive integer ends. So we have an infinite number of solutions. What do they do? Here was the problem. Each one of those solutions, each one of those infinite solutions, the solution to the equation itself, and also satisfies these two boundary conditions, temperature at each end. The thing we haven't accounted for yet is the initial temperature. By the way, this up here is just, you might need to be getting more used to that. If you have sine of something and equals 0, it means the something's an integer number of pi. If you have the cosine of something 0, it means that something is this thing. 2n minus 1 times pi. Anyway, we'll be doing more of that later in other examples. But for right now, how do we address this initial condition? We've got an infinite number of solutions that satisfy everything else. Here's where the superposition principle. Infinite linear combination of those solutions is also a solution. So the general solution is this infinite linear combination of, well, these are all those infinite solutions. It's the T part times the X part. Here is a general solution that satisfies everything except the initial condition. And actually what we want are all these coefficients, the A's and B's. If we had those, satisfy everything. How do we go about doing that? Well, the initial condition was at time 0, which means little t equals 0, this whole thing just becomes 1, and we're left with this. And that's what has to equal the initial condition. Here's where orthogonal expansion comes in. Well, there's different ways to expand this function. just using Fourier series or cosine series or sine series. If I expanded this function, and we really only care about it, this function from x goes from 0 to L. Let's say the function, just to demonstrate what it means, let's say the function is just x itself. Let's say this f of x is just x itself. So it would look like this. And it would only be defined from 0 to L. If I expand it using a full Fourier series, it would look like this. And in fact, this would be repeated an infinite number of times to the left and right, right? If I expand this function using a cosine series, it's an even function. I would get this from minus L to L, and then an infinite number of those outside of minus L to L. If I expand it with a sine series, it would look like this, an odd function, infinite number of clones outside of that. And all we care about is from 0 to L. So I could match this thing with any of these three expansions. We're going to use what's called a half-range expansion concept. What we want, though, is an expansion that matches this formula. That happens to be, in this case, the sine series. We're going to want to expand this f of x using the sine series. So we'll say u at time 0 was this thing. That equals our initial condition. And we're going to expand this initial condition using the sine series. It will look like this. So all we want is our a sub n equal these b sub n's. Just matching coefficients. And we have a formula for the b sub n's from our Fourier sine series. That was this. We now have a complete solution. The total solution is this. We already had that. Now we have what these a sub n's are. Got that from the sine series. If you wanted to, you could put that in all one big mess. You wouldn't have to. You could just say it's this where the a sub n's equal that. A little long here. Well, first let's do some example for that. Let's pick a specific example where that initial condition was just some constant for all x. We'll say the length of the rod was pi, k equals 1. Our a sub n's would turn out to be this from the formula. You can do that integral, you get this, and in fact, you get that. The total solution, well, I'm going through this very fast, but what we had on the previous chart, the total solution would look like this. You could look at partial sums. You know, don't sum it all the way up to infinity, but it's sum it up to some n, maybe n equals 15 or something. Or, you know, with this upper limit being maybe 15. And that's what was done here. These graphs are from partial sums of this guy. So let's look what happens. This first one is, let's see, uxt for various times. So this, along the bottom here is x itself. At time t equals 0, the whole thing was this constant 100. As soon as time equals 0, I clamp the temperature to be 0 at each end. And there's immediately this continuous jump in temperature at time t equals 0. It goes down to 0 at each end. It stays hottest in the middle, but as time goes on, as time gets bigger here, it's cooler all the way through the rod and eventually asymptotically becomes 0 all the way across the rod. This guy is u of xt, where this axis is for t, but for various x's. The highest temperature is in the middle of the rod at pi over 2 because the rod is in pi. Falls off fastest as you get to each end, that's where it falls off fastest. Anyway, that's what's going on with that solution. I think I'll do this last chart in another recording.